Thanks for coming back again. If you have subscribed, if you are yet to subscribe, you can click on the subscribe button and also on the bell beside it. That will notify you when we drop a new video. Thank you. In this video, we want to look at the differential calculus for MTH today, and we're going to start with differentiation from first principle. The reason why you have to watch this video to the end is that we're going to treat the most important aspect of differential calculus, and we're treating them from the simplest to the toughest. So that is the reason why you have to watch it to the end. That is one. Now, before we swing into the action or go deeply into differential calculus, I would need to make some symbols clear to us, because I discovered that these symbols are used interchangeably with one another, but which is actually wrong. I have the symbol this, and I have this. I have the capital letter D, the small letter d rather, and I have capital letter D. These four symbols are used in calculus, of which sometimes people use this in place of this in calculus. But however, I'm telling you now that this symbol is a Greek letter called delta. It is used to represent change or increment in a variable as far as calculus is concerned. And this one is used to represent the partial differential operator. Partial differential operator. The reason why it is called partial differential operator is that you might have a function of two variables, depending on two variables, x, y. So if I'm to differentiate this function with respect to x alone, then I'm going to use the partial derivative or the partial differential operator as a symbol, not the total differential operator. So suppose this function is equal to x squared plus y squared, and I'm meant to differentiate with respect to x alone. So the derivative of this function with respect to x will be denoted by df dx, and that of the function with respect to y is going to be what? df dy. So that is what partial derivative is all about. So now we can actually swing straight to the next one. So we have the D, which is called the total differential operator. This one is used to differentiate all through the variables in a function, provided it is a single variable. So like a function of f of x. So to differentiate this is very easy using the total differential operator. It does not consist of two variables. So the last one is called operator D. Operator D. It's pronounced D. It also have its use as far as calculus is concerned. It is the act of finding the derivative of a function, mathematical way of finding the derivative of a function with respect to x or any other variable. So now let us assume I have a function of y equals fx. Y equals fx. So if I'm to draw the graph for this, suppose the graph of this function is this, of which I have a curve. Let us pick 2 points from this curve. So take point P and point Q. If I join a secant, which is the line that cuts the curve to these 2 points, I would have a straight line AB, of which the gradient of the straight line could be calculated using this, of which here will be changing y, and here will be what? Changing x. So gradient m1, that is for AB. For AB is going to be equal to the change in y over the change in x. So now, don't forget the coordinate of point P is x. So the new coordinate at this point is, if this is x, or rather x naught, y this is x, and this is y naught, y this is what? Y. It implies that the new value of x here is the same thing as x naught plus the increment, which implies that if something is in 2, if a particular variable is in 2, then it changes to 6. So which implies that the exact change that has taken place is 4. So which implies that this 6 is going to be what? 2 plus 4. That is what that is talking about. So I have that. So also for y, I'm going to have y, the coordinate here is y rather. So here is going to be what? Y, which is equals to y naught plus change in y. So let's take it into consideration a function of this nature that I have x equals x naught plus change in x. So if there is a change in x, that must be accompanied by change in y. So let's consider this function that we have y if y equals fx. This is the function. So if there is a particular change in x, if this is x naught, then we add the change to it just like what I've explained here. It will be accompanied by change in y. So meaning we're going to have y plus change in y will be corresponding to f into x plus change in x. So and with this, I can explain this using the graph that any changes that takes place in y is accompanied by s. Suppose this point q moves downward. What will happen to change in y is going to decrease as can you see the height of change in y decreases. So and it also affects the change in x. So any change in y we correspondingly affect change in x, and also any change in x will correspondingly affect change in y. But however, I can still say x controls the function because it's an independent variable. We'll get there, don't worry. So now, at the same time, if I want to establish the value of my change in y here, I would have f of x plus change in x minus y. And minus y, meaning I brought this to this side, and y is equal to fx, so I'm going to have this. That's minus fx. So which implies that change in y equals this. So at the same time, I told you that any changes, considering the gradient now, like I've said, the gradient of this second, m1 will be this, so meaning change in y, the gradient will be equals to this. The gradient of the second, AB, from point P to Q will be given by this, according to what we have here. So now, how do we find the derivative of this function? Suppose I have said earlier that Q moves downward, and it continues doing that until an extent whereby if change in y decreases further, change in x will tend to 0. In what context? Because of this line forms a tangent with point P. This line which forms a tangent with point P here, once change in y decreases further and it affects it, there is tendency you are unable to find the remaining or the value of change in x again, then it's close up with the tangent. So at this point, we can say that we have reached the limit of which y could change further. So the value of change in x has affected the change in y now, in the context that if there is further decrease at this point, at this particular point, we would not be able to read our change in x, so we assume it tends to 0. So that is the limit. So at this particular point, we can say that that is the derivative of that function. So which implies that the gradient, don't forget that once there is a change affecting y, it must affect x, just like we have here. So and as it goes, the gradient m1 begins to move closer as to change in x tends to 0. So meaning that what I have here equals m1. So and the new gradient here at this point where change in x tends to 0 will be the derivative of the function, because it implies that m1 tends to m2, which is the new gradient at this limit. So the new gradient at that limit m2 will be written as dy dx, which is the derivative of y with respect to x. The effect of change in y, or rather the effect of change in x that affects y, and the limits at which change in x tends to 0 is what we call dy dx. So if I'm going to write that now, I can say that dy dx is the limits as change in x tends to 0. The limit as change in x tends to 0 of change in y all over change in x. So, meaning that the gradient m2 is gotten as the gradient of m1 tends to. So, that is what the explanation is all about. So, what we do here is what we call the differentiation from first principle. So, which implies that the dy dx of the function is equals to the limit as change in x tends to 0 of what we have here, which is f of x plus change in x all minus fx all over change in x. So let's go for an example to do this mathematically following this formula. If I am going to find the derivative of a given function without using this graph or whatever, just mathematically, how am I going to get? If y is equals to 2x squared, I'm meant to find dy dx from first principle. How am I going to do that? Don't forget the formula says the dy dx is the limit as change in x tends to 0 of f of x plus change in x minus f of x all over change in x. So we're going to follow this. So which implies that I'm going to solve this. We're going to have y plus change in y equals 2 into x plus change in x, just like what we have here. So then what next? According to the formula, I have to subtract fx from both sides. Don't forget y equals fx. So if I'm subtracting 2x squared from this side, don't forget we have squared here. I'm going to subtract y from this side. So which implies if I subtract y from this side, I'm going to change in y. And that will give me 2x plus change in x all squared minus 2x squared. So then what next? I can actually simplify what I have here. If I simplify this square, so I can proceed, I would have 2 into, that is x squared plus 2x change in x plus change in x squared after expansion minus 2x squared. So which implies that I would have 2x squared plus 4x change in x plus 2 change in x squared minus 2x squared. As these, we automatically go with this. So which implies that my change in y is equals to 4x change in x plus 2 change in x squared. So the next line of action is to divide all through by change in x. So that is the next line of action. So I do that. So which implies I will have change in y all over change in x equals the 4x plus 2 change in x. And don't forget, I'm looking for the derivative as change in x tends to 0. So there's next line of action. So I will say that as change in x tends to 0, then we take all the change in x and we take them to be 0. So then this will become the derivative. The gradient of the seconds, which is this. Once this is turned to 0, change in x in the expression is turned to 0, then we're going to have 4x plus 2 into 0. So at this point, we call it the derivative. So we have dy dx equals 4x. So and that will be the derivative of the function. Yeah. So let's take another question. So just reframing what I have here, I can just say if y equals root x. So let us use the word, let's use root x. So from there, we apply this solution, which implies that y plus change in y is going to be what? Root x plus change in x. So and at the same time, I would have change in y equals the root x plus change in x minus root x. At this point, we have to simplify before we go further. So we've done what is there in the numerator. So the next thing is, let us try to rationalize this expression. So this is over 1. So if I multiply that by root x plus change in x plus root x all over root x plus changing x plus root x. So this will give me automatically, this will multiply this, and this will give me what is here. So this times this gives me x plus changing x, and this times this gives me root x into root x plus changing x. Then this goes with this, I have minus root x into root x plus changing x. Then this goes with this, I have minus x. That will be all over what is here times 1, which is x plus changing x plus root x. So automatically this goes with this. At the same time, this goes with this. So I will be left with changing x all over the root x plus changing x plus root x. So from here, what next? What would I do? I can now continue with the step by dividing all through by changing x. So if I do that, meaning I'm going to have changing y by changing x, that will be times 1 over changing x. And that will give me 1 here. So if that gives me 1, what next? I'll be left with changing y all over changing x equals 1 all over the root x plus changing x plus root x. So of which we can actually say, okay, the limit as changing x tends to 0 will now be the dy dx. The limit, the dy dx now will be equal to the limit as changing x tends to 0 of 1 all over root x plus changing x minus root x. So that implies I would have the y dx to be 1 all over root x, plus root x. And that gives me 1 over 2 root x. And that will be the derivative of that function. There is always a way out of doing this apart from first principle. There is always a way out, so it implies that all functions fx are always probably in their polynomial form, so we have a x raised to the power n. So we say all functions can generally be in this form. So the derivative, which is the y dx, which you can rather call the differential coefficient, or the derivative, or something denoted by this, or which is also denoted by this. And at the same time, if this is equal to y, so we can also call this y prime. So the derivative of which we define with all these symbols for a general form of polynomials here, we're going to have them, of this expression rather, we're going to have them to be a n multiplied by x raised to the power n minus 1. So this is a general formula generated from first principle. So meaning that if I am to solve these, y equals ax raised to the power n, from first principle, what I would have is this. Yeah, if I solve this from first principle in general, this is what I would have. So this has now become the formula to differentiate a function. Without first principle. So now let's try it for the previous ones we did from first principle. So which implies that if I have y equals 2x squared, the 2 here is the a, y the power, which is the square here, is the n. So according to the formula, if I say 2 times n, that will be 2 times 2. Then x raised to the power n minus 1, that is 2 minus 1, that is 1. So which implies that we have 4x. And that is very simple. So if I do that for y equals with x also, which implies that this equals x raised to the power half. So the coefficient here is 1, which is a. So meaning I'm going to have 1 times half, which is half. Then subtract 1 from half, and that would give us x raised to the power minus half. So if I would express this in what I had before, that would be 1 over 2 times 1 over x raised to the power half. And don't forget x raised to power half is root x. So I have 1 over 2 times 1 over root x. So multiplying the numerator with the numerator and denominator with the denominator, I'm going to have dy dx equals 1 over 2 root x, which is also equivalent to what we got the other time. So I think the formula goes a long way. So now, what is the use of this formula? What is the use of this formula? Imagine I am to differentiate a polynomial. That is differentiation of polynomial. I am to differentiate the polynomial y equals 3x raised to power 4 plus 2x raised to power 3 minus 4x squared plus 3x minus 1. This is a polynomial. If I'm to do this from first principle, I'm going to take a lot of time. So the formula is best used in this process, which implies that the derivative of y with respect to x will now be, I will find the individual derivative. I'm going to use the formula to find the derivative of individual expression. So by doing that, using this formula, we're going to have the 12x cubed plus 6x squared minus 8x plus 3, and this will be 0. This will be 0. The derivative of constant, which is minus 1, is 0 center. That will be the derivative of this function as it is now. So now let's quickly move to the rules of differentiation, because however we've talked about the first principle, there might be some complex function that will require special approach to solve them. So there we have to talk about the rules of differentiation. The rules of differentiation. So we have the chain rule, we have the product rule, and we have the quotient rule. The quotient rule. So these three rules will be treated and will be used in advance in trig differentiation, because we are going to treat that also in this video. So now, taking the chain rule, in what cases do we use chain rule? We use chain rule where we are meant to differentiate a function of function. What do I mean by function of function? If I have f to be function of u, y to be function of u, and at the same time u is a function of x, so which implies that indirectly y is a function of x. In a layman language, I am the boss of someone, so he is under me. Then he also has somebody who he is the boss to. So indirectly, I am the boss of the person under him. So y is the boss of u, and u is the boss of x. So indirectly, y is the boss of x. So if I'm now to find the derivative of y with respect to x, how am I going to do it? Don't forget that y is the function of u. So the chain rule states that to do that, that means to find the y dx, or probably y prime, that would be equal to the dy of the u times the u of the x. So that means that I'm differentiating y with respect to u, and I'm multiplying that with the derivative of u with respect to x. So we are looking at it, this, we cancel this, and I would have the y dx directly. So let's take that into practical or into a question. So which implies that if I have y equals 2x squared plus 1 or raised to power 3, and I'm meant to find y prime, which is the y dx. And I told you it can be represented by this. So to do that, I would say let u equals 2x squared plus 1. So if u is 2x squared plus 1, that means y is what? U cubed. So the derivative of u with respect to x, that is du dx, is going to be equal to the derivative of individual here, which is 4x plus 0, and that is 4x. So the derivative of y with respect to u will now be 3u squared. So that the product of the two would give me my dy dx. So dy dx will be this times this, which is 12x u squared, and that will be 12x. U is 2x squared plus 1, so I have 2x squared plus 1 all squared. You can simplify this further, that is after you expand this, then use this 12x to open the bracket. However, all these rules will still be applied in trig and exponential differentiation, which we are going to do in later parts of this video. So now let's proceed with that. Y equals 5 all over the square root of 1 plus x squared all raised to the power 3. So if I have this, I'm meant to find y prime. How do I go about that? So what I'll do is I'll have to change the expression to that of the previous one we solved. So, and that would give me y equals, this will be 5 multiplied by, that is the root of 1 plus x squared all raised to the power minus 3, and which is the same thing as 5 multiplied by 1 plus x squared all raised to the power minus 3 over 2. So which I've turned into what I want. So and that will give me y equals 5 into 1 plus x squared all raised to the power minus 3 all over 2. So I can now say that let u equals 1 plus x squared. So that y will be what? 5u raised to the power minus 3 over 2. So finding the derivative of u with respect to x, that is du dx. And that would give me 2x, just like derivative of 1 is 0. So then the y of the u will be equals to minus 15 all over 2 u raised to the power 5 over 2 rather. So that will give us minus 5 all over 2. Please subtract 1 from minus 3 all over 2. That will give you minus 5 all over 2. So in this case, what would I do? I'll have to multiply the 2 together to get my dy dx, which I can actually do here. So dy dx will be 2x multiplied by, or let's say into brackets of minus 15 over 2 into u raised to the power minus 15 over 2 u raised to the power minus 5 all over 2. So this goes with this, so I have minus 15x u raised to the power minus 5 over 2, and that will give us minus 15x times 1 over square root of u all raised to the power 5. So, and this gives us the minus 15x all over u now becomes 1 plus x squared, so 1 plus x squared all raised to the power 5. So that is the derivative of this function. If I have a function of y which is equal to f of x, and the f of x is a product of g of x, so which implies that y is a function of two functions. F is a function, y is a function of x multiplied by another function which is g of x. So product of two functions. So if we call this u and we call this v, so which implies that y is equal to what? ub. So to find the derivative of y with respect to x in this context, the rule says the y dx is u dv dx plus v du dx. U multiplied by dv dx and plus v multiplied by what? du dx. So let's look at the question on that. So the question I'm going to solve on that is, if y equals 2x squared plus 1 into s cubed plus 3x plus 2. So then I can say that this is u and this is v. So u equals what? 2x squared plus 1, and v equals what? S cubed plus 3x plus 2. So according to the formula that says dy dx equals the u dv dx plus v du dx, then I will say that u is this this. So I would find dv dx and du dx. dv dx will be the derivative of b with respect to x. So dv dx will be the derivative of individuals here, which is going to be what? 3x squared plus 3x. Sorry, plus 3. As derivative of 2 is 0. So then we are going to have du dx also, which is the derivative of this. So du dx is going to be equal to 4x as the derivative of 1 is 0. So now we slot them all into these formulas to have our dy dx, which will be u, and that is what? 2x squared plus 1 multiplied by dv dx, which is this, that is 3x squared plus 3, then plus v, which is this, that is s cubed plus 3x squared plus 2 multiplied by du dx, which is the derivative of this, and that is 4x. So we can expand this and also open the bracket here, then collect the like terms and solve out. So if we do that, this is going to give us that is 6x raised to the power 4, then plus 6x squared, and this will give us plus 3x squared, and this will give us plus 3. If I expand it through, and this would give us the 4x raised to the power 4 plus the 12x cubed plus this 8x. So collecting like terms, I'm going to have this join with this, and that will give us 10x raised to the power 4. And this will give us, if I have anyone with squared, I think this gives us, I can arrange in order. So I'm going to have 12x cubed. Then I'm going to have to add the squares together. So and this gives me plus 9x squared. And I'm going to have the 8x plus 8x plus 3. I think this is the derivative of this function. According to quotient rule, the quotient rule states that if I have a function y equals u all over v, that is the quotient. So dy dx is going to be equals to v du dx minus u dv dx all over v squared. So I have a function y equals x squared plus 1 all over x minus 1. How do I solve this? U is going to be equals to x squared plus 1, and v is going to be what? X minus 1. That is the up and the down. So what next? Don't forget we have the formula. We need the du dx. So the u dx will be the derivative of this, and that will be 2x as derivative of 1 is 0. So then we have dv dx also, and that will be equals to 1. Derivative of minus 1 is 0. So slotting that into the formula here, I'm going to have the y dx is going to be v, which is x minus 1, into the u dx, and that is 2x minus, then I'm going to have u, which is x squared plus 1, into dv dx, which is 1 all over v squared. And what is v? X minus 1 all squared. So then I can simplify this expression to what I want. So and that will give me the 2x squared minus 2x minus, don't forget this should be in parentheses. So that will be minus x squared plus 1 all over, this is x minus 1 all squared. And this gives me 2x squared minus 2x minus x squared minus 1 all over x minus 1 squared. And that gives me dy dx will now be equals to 2x squared minus x, so that gives us x squared minus 2x minus 1 all over x minus 1 all squared. Implicit differentiation. So what do I mean by implicit? Implicit differentiation. The derivative we've been finding all through from the beginning of this video to this point are explicit functions. So we can also have implicit functions. An example of an implicit function is if we have x, y plus 2x, y plus x squared, y squared equals 0. We should find the y, the x. So implicit function contains the variable y itself. So this is not actually partial derivative, but we call it explicit differentiation, where we are about to differentiate all three functions. So let's go ahead doing that. So to find the derivative of this function, what do? We can take the derivative of all expression. So and that would give us the derivative of this is 1, that is for x. The derivative of y is also 1, but when you differentiate y in implicit differentiation, you replace it with the y dx. So and that gives us dy dx all through here. That is 1 multiplied by dy dx. 1 for the x, and 1 times 1 is 1. So 1 also for the y. So everything just gives dy dx. So and then plus, if I differentiate this is 2xy. So and that will eventually give me, if I differentiate 2x, and that will give me 2. And that will be 2 dy dx. And if I do that here, I'm going to have the 2x dot 2y dy dx all equals to 0. So which implies that I'm going to have dy dx plus 2 dy dx plus 4xy dy dx all equals to 0. Excuse me. So if I factorize, bringing out the common factor, which is dy dx, I'll be left with 1 plus 2 here, and this will be plus 4xy all equals 0. So 1 plus 2 will give us 3. So which implies that I'm going to have dy dx into, this is 4xy plus 3 all equals to 0. So that implies that my dy dx is going to be equals to 0, because if I divide all through like this, and that will give me dy dx would be equals to 0 all over 4xy plus 3. So dy dx in this particular question is going to be 0. So we can take another explicit function. I think I have them here. So let's take one more explicit differentiation question and see how we solve it out. So we will have xy equals 1 here. There is a question that says if xy, I'm going to take one more after this, equals 1, find dy dx. So this is so much simple. So which means what I'll do is, this is product, so I have to use product rule. Since it's an product rule says that dy dx is v du dx plus, u dv the x plus v du dx. So which implies that I will take this as my u, and I will take this as my v. So if that is the case, what I would do, then I will follow the formula u, that is x, dv dx, the derivative of y, which is dy dx. The derivative of y will give us 1 dy dx. That will be plus v, which is y. Then the derivative of x, and that will be 1. All equals, the derivative of 1 will be 0. So if that is the case, I will have x dy dx plus y all equals 0. So bringing y to the other side, I have x dy dx equals minus y. So that dy dx is going to be what? Minus y over x. So that is the derivative of this function. So if y equals x raised to the power x, how do you think we can find the derivative of this? Okay, let's do it this way. If I take the Napierian logarithm of both sides, I'm going to have the inertial of y equals the inertial of x raised to the power x. And that would give me the inertial of y equals x multiplied by the inertial of x. So finding the derivative of both sides, and this is one of the rules you need to know. The derivative of the inertial of any variable with respect to x is equal to 1 all over that variable. I'm going to have the 1 all over y here, but don't forget it's x implicit, so I have to make it the y dx. All equals, I'm using the product rule here, and that will give me x, the derivative of this, which is 1 over x, plus, according to the product rule, the derivative, the next into the derivative of x, which is 1, and that will give us 1 over y dx, all equals 1, please cancel this, plus what? The inertial of x. So if I multiply both sides by y, I'm going to have the y dx here, and that will be equals to 1 plus the inertial of x, all multiplied by x raised to the power x. So I think this would be the answer of that question. So we can solve more as much as possible. So let's look at this another question here that says we have y equals 2 raised to the power the inertial of x. Y equals 2 raised to the power the inertial of x. So how do we solve this? So I think we use the same approach. So taking the inertial of y equals the inertial of 2 raised to the power the x. So I think that gives us the inertial of y equals inertial of x dot inertial of 2. So with this, I can say the inertial of y equals inertial of x. This is product, so definitely we're going to have the inertial of x plus 2. X plus 2. So here I'm differentiating here, and I'm also differentiating here using the chain rule. So the derivative of this is 1 over y dy dx, and the derivative is going to be, to find the derivative, let's do that in one corner. So we have in x plus 2, so x plus 2 will be u. So if this is equals to a, so that means a equals what? Inertial of the inertial of u. So to find the derivative of this, and that will be the derivative of this, which is 1, multiplied by the derivative of this, which is 1 over u, and that will give us 1 over u. Or in direct, you can say the derivative of this is 1 over u. So that gives us 1 over x plus 2. Since what? U equals x plus 2. So which implies that the y dx would be equals to 1 over x plus 2 multiplied by what? 2 raised to the power inertial of x. So and that is what? 2 raised to the power inertial of x all over x plus 2. That's the derivative of that function. Transcendental differentiation. We call that transcendental differentiation. I have to give some standard derivative to understand this. So, which implies that if I have a function of x, the derivative, which is this, will be what? So now, and I will start with sine x. The derivative is cos x. This can be proved from first principle. Then we have that of cos x, and that will give us minus sine x. We have that of tan x, and that would give us the sec squared of x. All these can be proved, as I would love to prove this, that of tan x, and so on. So we'll have also the derivative of cos, and so on. But however, I've said this earlier, the derivative of min x, or sometimes called the log e of x. will be 1 over x. And also the derivative of e raised to the power ax is going to give us, find the derivative of the exponential of the power, so meaning I'm going to have a e raised to the power ax. That's the derivative. So we also have for sine arc of x, cos arc of x, tan arc of x, and many more hyperbolic functions rather. Hyperbolic functions also have their own derivative, of which we could apply them in this context. So, and also I want to say this in additional, the derivative of 2 raised to the power x is going to give us 2 raised to the power x into 2 raised to the power x in 2. So that is the derivative of 2 raised to the power x. So which implies, or probably I said, I put it in form of a raised to the power x because it sometimes might not be 2. So, and that will give us a raised to the power x in a. So these are standard derivative. We still have more of this that we could use. We can actually prove these ones. We can prove this one before the end of the video. We will prove these 3 so to get their exact value. So these are standard derivatives that are used in solving various questions. So let's see how they are applied. Sometimes how they are applied. So let's look at 5 questions based on this before we prove these 3. Take for instance, find the derivative of the following. So if the first one is y plus tan x, so which I've said I will prove that. Okay, and I have y equals sine arc of x, and I have y equals the cos arc of x, and I also have y equals the tan arc of x, and I also have v, which is probably y equals cos 3 all over 4x squared. So let's take it this way. Then we can take the last one, which if I say that y equals the cot 2 all over 3x. So let's answer this for question. Then after these 6 questions, so after these 6 questions, I think we should be able to answer just a little bit tough questions more. Then we proceed. Solutions. The first one says y equals tan x, so I have y equals tan x. You should believe me that tan x is the same thing as sine x over cos x. So y equals the sine of x over the cos of x. Which implies that if I am to differentiate this, it's going to be with quotient rule. So if this is u, this is u, and this is v, using the quotient rule, dy dx is going to be equals to v du dx. V is cos x. Du dx is the derivative of sine x, which I also said is cos x, minus u, which is sine x, multiplied by the derivative of cos x, which I said is minus sine x. Don't forget this is quotient rule, all over v squared, which is what? Cos squared x. This would give cos squared x plus this product will give us positive, and I also have sine squared x all over cos squared x. From trigonometric identity, cos squared x plus sine squared x is 1 all over cos squared x. So which implies that 1 over cos squared x is sec. So 1 over cos x is sec x rather. So meaning that 1 over cos squared x is then what? Sec squared x. So this has proved that the derivative of tan x is sec squared x. The second question says that y equals the sine arc of x. With what I have here, I can say that x will also be sine of y. If x is sine of y, then the x dy, which is not dy dx, will be the derivative of sine y, which will be what? Cos y. And that implies that the x dy rather, then dy dx will be inverse of this. That's 1 over cos y. So how can I change this expression from y to x? You believe me that in trig identity, we have that the sine squared y plus cos squared y is equals to 1. Cos squared y is equals to 1 minus sine squared y. And that means cos y will be square root of 1 minus sine squared y. So if I take that into this, cos y will become this. So I'm going to have 1 all over square root of 1 minus sine squared y. And don't forget, sine y is equals to x. So which implies that dy dx will be equals to 1 all over 1 square root of 1 minus x squared. Since sine y is equals to x, so sine squared y will be x squared. So that will be the derivative of sine arc of x. Then we also have for cos arc of x, which will follow the same process. And this will be cos arc of x, and x will now be cos y, so that the x dy will be minus sine y, like I've said in the table that the derivative of cos is minus sine. So that this will be minus 1 all over sine y. So that this will now be sine y, sine squared y rather, and this will be cos squared y. And this will be sine y, and this will be cos squared y. So which implies that dy dx is equals to, if sine y is this, I'm going to have 1 all over square root of 1 minus cos squared y. And that would give us, since x is cos y, dy dx to be 1 all over 1 1 minus what? Don't forget this, that's minus 1 in negative. So I'm going to have square root of 1 minus, then cos y is x, so I'm going to have x squared. So and that is the difference between the derivative of sine arc x and cos arc x is this negative 1. So and that is that. So let's quickly look at that of tan x, so it can also follow the same trend. So but we're going to use different identity for this. So which implies that this is tan arc of x. And if this is tan arc of x, x will be tan of y. So and in that case, the x dy will be sec squared of y, which we have proved in question 1. So and if that is the case, what next? Dy dx would be 1 all over the sec squared of y. Don't forget an identity that says that if I have sine squared y, plus cos squared y, it gives me 1. Suppose I divide the expression by cos squared y. So I'm going to have cos squared y here, and I'm going to have cos squared y all over cos squared y. And this would give me the tan squared of y plus 1 equals the sec squared of y. So which implies that sec squared of y is equals to tan squared of y plus 1. So I'm having dy dx equals 1 all over tan squared of y plus 1. And tan y is x, so which implies that this is equals to 1 all over x squared plus 1. So, and that's the derivative of tan arc of x. So let us check the remaining two before we call it a day. So if we proceed to this, I'm going to have y equals the cos 3 over 4x squared. And here I'm going to use the chain rule. The chain rule. So in the chain rule, what I'm going to use is, I'm going to say that let u equals 3 over 4x squared. So that y will be what? The cos of u. So the derivative of these two and multiplying it with each other will give us the derivative of y with respect to x. So the derivative of y with respect to u is minus sine u. So dy du is equal to minus sine u. That is the essence of that table. So then here I have du dx, which is going to be this times this, and that is what? 3 all over 2x. So the product of these two, which is dy dx, is now minus 3 all over 2 sine, minus 3 all over 2x rather, sine u. And u becomes 3 all over 4x squared. So that gives us minus 3 all over 2x sine x squared. So, or probably sine squared x. And that is sine x squared rather, in brackets. So that is for that. As simple as that. So let's move to the cot 2 all over 3x. So if I have y equals the cot of 2 all over 3x, what I'm going to do here is also chain rule. So that let u equals 2 all over 3x, so that y will be what? The cot of u. Then I find the derivative of this. So I'm du dx will give me 2 all over 3. So the derivative of cot u now is what we need to find. So once we find this, you can put it into the table and memorize it. So, and that gives us, don't forget, we have y equals 1 over tan u, and that will give us cot u. So using the quotient rule here, we can find the derivative. So the quotient rule says that this is u and this is v. So v, that is tan u, du dx, which is 1, that is 0, minus u, which is 1, dv dx, which is sec squared u rather, all over v squared. And v squared is what? Tan squared of u. So which implies that the answer here is going to give us, what is here is going to give us what? 0. Tan u multiplied by 0, that will give us 0. Then that will be minus sec squared u all over what? The tan squared of u. So if I'm to express this in a very, to simplify that, or probably let me find the product of the two, and that is the y dx, would be 2 all over 3 times minus sec squared u all over tan squared u. And what would happen? I'm going to have minus 2 sec squared u all over 3 tan squared u. So I can simplify this further. Don't forget that sec squared u is the same thing as 1 all over cos squared u. And at the same time, tan squared u is the same thing as cos squared u all over sine squared u. So I can still separate this, and meaning that I'm going to have minus 2 all over 3 multiplied by, this will be 1 all over cos squared u multiplied by, that will be sine squared u. That means if I'm dividing this by this, so 1 over this divided by, okay, let's write that first, divided by the cos squared u over sine squared u. So which is automatically giving me, let's continue here, minus 2 all over 3 into 1 over cos squared u times sine squared u over cos squared u. And that will give me minus 2 all over 3, and that will give sine squared u all over, that is cos squared, or cos raised to the power 4u. So which could be expressed or simplified further, but I would love to leave my answer like this, and that would give me, or probably sometimes leave it the other way around. So I'm going to have minus 2 sine squared, u is now 2 all over 3 x. So I'm going to have sine squared 2 all over 3x all over, that's 3 into cos 4th power of 2 all over 3x. So this is the derivative of that function. If I have the cos arc of 3x plus 2 all over x plus 1. How am I going to solve this? Don't forget, all this equals y. So to find the derivative of this, what am I going to do? It's very simple. I'm using the quotient rule and the chain rule all together. So and that is equals y. So let u equals 3x plus 2 all over x plus 1. So meaning that y is what? The cos arc of u. So and I've said earlier, we'll find the derivative of this and also find that of this. So to find the derivative of this, that's dy du. And that would give us, like I've said earlier, minus 1 all over square root of 1 minus x squared. That is the derivative of cos arc of u. So after finding this, I will have to find this using, I don't have to prove this anymore, which I've done. So what I would need to do is to find the derivative of this, and that would be by quotient rule. So if I would do that, du dx will now be, I'll take this as v, and that is this as u and this as v. So I'm going to have x plus 1 multiplied by the derivative of this, that is 3. Then what next? Minus, I'll take this, that is 3x plus 2 in brackets, derivative of this, and that is also 1 all over v squared, and that is x plus 1 all squared. 3x plus 3 minus, this will be 3x minus 2 all over, this will be x plus 1 all squared. And this minus this gives 0, and I'm going to have 1 all over x plus 1 all squared. So the product of these two, using the quotient rule, the chain rule rather, the product of these two, which is this and this, will give us our answer, and that is the y dx will now be this times this, and that will be 1, that's minus 1 all over the root of 1 minus x squared multiplied by x plus 1 all squared. So, and this would be the final answer to that question. Thanks for watching. If you like what you see, and click on the subscribe button, click on the bell beside it to notify you when we drop a new video. Thank you.